in addition to the University of Houston group, also the University of Alabama at Huntsville, and also C.Y. Huang at Lockheed Research Center. In today's discussion, I'm going to present it in the following order. First, I'm going to describe very briefly from 30 degrees to 90 degrees, and then the discovery of the new class of material expressed by this formula. And also, I'm going to emphasize the difference between the lanthanum-barium the 214 phase, the single layers phase, and also the 123 phase. And then we question, where is superconductivity in the 123 phase? In that discussion, we measure the magnetization versus field, and also did some ESR measurements, and also did some preliminary alloy measurements. And then I'll conclude the talk with brief remarks. I think at the beginning, after Bednock's and Alex Miller's measurements, we decided to look at, after we reproduced their results in about the same time like the Tokyo group, we decided to look at what's happening in this material. So we subjected the material under high pressure, and we found that it has an unusually large pressure effect in the single layer structure, which is about 100 times bigger than the ordinary superconductors. And then we know that pressure only will reduce the interatomic distance. So try to simulate the pressure effect. We substituted with chemical methods. For example, with strontium, replacing barium with strontium, which has small atomic radius, like also done by other groups. We found the TC actually went up to 42.5 degrees without the application of pressure. But then later on, we further reduced it with calcium. The TC drops to 20, as Professor Tanaka already showed. So based on this, we realized that the mere reduction of interatomic distance is not going to lead us to higher temperature. We do know the importance of atomic radius from these studies. And also, we look at the transition width of the known materials. When the materials is made into a single-phase potassium-2 nickel fluoride structure, the onset temperature always drops. And by that time, we also observed sign of superconductivity at above 70 degrees in many materials. And based on that result, but only in those materials with the four phases in addition to the single layer structures. So from here, we concluded that TC above 70 degrees will occur, but only in non-nickel fluoride, potassium nickel fluoride structure, and perhaps new compounds, preferably with yttrium and scandium replacing lanthanum, will work. Because these two are, based on the pressure study, we realized that atomic radius is extremely important. So from that, we finally, on January the 29th, we observed this curve. And it started to drop at about 98 degrees. It went to 0 at 80 degrees. And then later on, we also looked at the magnetic effect on this material and did some AC susceptibility measurements and showing the Meissner effect and also eddy current effect, the shielding effect. In a few days, we improved the material and we narrowed down the transitions, and also starting from 93 degrees and ends at 90 degrees. But then a few days later, we found that the onset is going to be 98 degrees and finishes at 94 degrees. So we did the ESR measurement, and you can see here for the yttrium barium copper oxide, you do see two little peaks indicating that there are two sides, at least two sides for the copper atoms. Okay, you can see little two things here corresponding to G equal to 2.08 and 2.15. And then we doped the material with the gadolinium in it, about 0.5 atomic percent, and you can see this, the gadolinium contributions from this residence line, and you can see the G is approximately equal to 2.3. So there is interaction between them. Okay, based on that, let me just conclude. And we also did the following. We look at the yttrium strontium copper oxide, but so far we have not been able to make it superconducting, although we got the majority phase to be 1, 2, 3 phase. If this is true, perhaps the strontium is too small to accommodate the oxygen in the strontium layer. If that is true, then the octahedral oxygen must be important in contributing to superconductivity. And then we also try cerium, and it doesn't work. This is possible that cerium is too large, but of course it can also go into the +4 phase. If that is the case, then the quasi-two-dimensional character may be important. We all know it's very important. So in conclusion, with a superconductivity above 90 degrees occurs in this kind of layer assembly, and the copper O2 layers interact with the A layers through, although very weakly. And the oxygen in the A layers are important. And then quasi-two-dimensional characteristic must be important. And glassy state has been observed in this material, but we don't know whether it's intrinsic or extrinsic. This has some implication and application. And also, we observed some antiferromagnetic interaction. And switching, we also saw that, and high TC is possible. And we also made the material magnetic phase, and we also make it into insulating phases. So just this. I think after all this rush, perhaps it's about time to slow down so we can study and enjoy the beauty of physics, chemistry, and material science in this wonderful class of materials.
If I understood you correctly, you claim that both tetragonal and orthorhombic varieties of the 1, 2, 3 are both superconducting. Have you prepared those phases pure? What experimental evidence do you have?
Because right now what we have seen is that we, depending on the heat treatment, apparently we can see some material which also has orthorhombic symmetry, but some of the material, based on, of course, it's only powder diffraction pattern, shows tetragonal symmetry, and yet they are still superconducting, and that's why I made that statement.
The mixture is superconducting.
Mixture? No, this is all single-phase material. Single-phase material, based on our powder diffraction pattern.